Mr. B. Dhanasega is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. Here we are having the subject called compiler design. So, as far as the previous episode is concerned, we have studied the regular expressions, and then that is we have seen the finite automaton. There are two types of finite automaton. One is the deterministic version and another one is the non-deterministic version, and they are actually used for designing the lexical analyzers. So, we have seen that there are equivalences among the deterministic finite automaton and the non-deterministic finite automaton. When you are given a non-deterministic finite automaton, it could be transformed into a deterministic version by using the subset construction algorithm. We have seen one example also how the NFA was converted into its equivalent deterministic version. So, with that actually the lexical analyzer component is over, and now we are having the syntax analyzer. That is going to be the second phase of the compilation. So, normally the syntax analyzer and lexical analyzer are working as coroutines. So, whenever there is a need for a token by the that is a parser, it will talk to the lexical analyzer and it will return the lexical analyzer in turn will return the token by reading the input from the source program. So, that is what normally happening. So, what is happening as far as the syntax analyzer is, it will just combine the tokens in the order in which they are received from the source program, that is from the lexical analyzer, and will check whether the pattern is going to be the one accepted by the source language specification or not. If they are accepted by the source language specification, then your parser will construct a parse tree whose definition is yet to seen. So, the parse tree is, if it is produces output, then we claim that the syntax of the source program is same as the specification of the language, and if the parse tree construction fails, then it will produce a no output saying that the program has some error. So, that is what the job being done by the syntax analyzer, or otherwise we call it as the parser of the compilation process. So, the definition for parser is, parsers are actually designed for some grammar. So, the grammar actually there it is going to be the tool used for describing the syntax of the source program. I mean the syntactic constructs of the source program. It can be either expression or a statement or a function or the entire program itself. So, the parsers are constructed only for the grammar, which may be a simple one or a complex one depending upon the type of constructs being generated. And once the parser has been constructed for a grammar, then the parser is expected to recognize the set of all strings which will be considered as the language of the grammar. So, for every grammar there is a language, that is nothing but the set of all strings recognized from the starting symbol of the grammar, and all those strings must be recognized by the parser. So, every string available in the language of the grammar, if it is given as input for the parser, then it will be converted into its equivalent parse tree. The construction of the parse tree will succeed because the string is already there in the language. And for example, if I am giving a string which is not there in the language of the grammar, then the construction of the parse tree will definitely fail, because it is not going to be accepted by the parser. So, the output, that is your definition, says a string w is taken as input and produces a parse tree for the string w, provided w is a sentence of the grammar G, or it will give you an error message indicating that w is not a sentence of G. And the grammars are actually used for specifying the syntax of the programming language constructs, including expressions, declarations, statements, etc. So, when you look at the role of the parser, so the parser lies here. So, the two different, that is adjacent components are, as a predecessor we are having the lexicon analyzer, which is always preceding the parser, and the output of the parser will be given as input for the intermediate code generation, which will generate the intermediate code from the source program. And you can see that there is going to be a link in between your lexicon analyzer and the parser, which is on bidirectional. Whenever a parser needs a token, it will request the lexicon analyzer with the message called get next token. On successful generation of a token by the lexicon analyzer, it will give a token as input for the parser, and on completion of the parsing process, we will be having a parse tree, and the parse tree will be given as input for the rest of the phases available in the compilation steps, which is actually followed by a semantic analyzer, then followed by intermediate code generation and optimization as well as code generation. But when you are looking at this diagram, we find another component that is called a symbol table. So, we will be having entries for every symbol, that is identifier into the symbol table, so that it will be referred by the parser as well as the remaining phases of the compilation. So, we have this link from lexicon analyzer to symbol table, we have link from parser to symbol table, and then we are having link from even the remaining phases to the symbol table. And all these links are seems to be, that is the bidirectional. It is because of the lexicon analyzer writes and verifies, parser writes and verifies. Similarly, the intermediate code generator, semantic analyzer, they all will that is have access for the symbol table. So, for example, suppose if you have an expression called a plus b, and the semantic analyzer, which is just following the parser, has to check whether a and b are compatible for the arithmetic plus or not. So, if you find both a and b are pointers, then only the semantic analyzer will detect that two pointers cannot be added. But how does the semantic analyzer find a and b are pointers? So, it will talk to the symbol table, or it will interact with the symbol table to know what is the type of a and what is the type of b. So, once it knows that both a and b are pointers, the semantic for the pointer says that two pointers cannot be added. So, it will report an error, that is your semantic analysis will report an error rather than the parser reporting an error. So, that is the reason why we have a symbol table component, and in addition with that, normally we will be having an error recovery, that is error routine, the reporting component, which is not that is presented here. So, that will tell you about the various errors being detected by the lexicon analyzer, the parser, and by the remaining phase of the compilation. So, that is what the role of the parser. So, now looking at the parser, we have already seen that what is going to be the simple role of the parser. So, it will parse the source program to find out whether there is any error in the source program as per the specification of the language. If there is no error, it will report or it will produce a parse tree as output, and if there is an error, it will say that parsing generation is not successful. So, that the programmer will be forced to correct the error, and then the continuation of the compilation will continue to produce the object code. So, now how the parse tree is constructed? Even though we say that the parser constructs the parse tree, so how the parse tree constructed, that differentiate how the parsing is done. There are two major classifications. One is going to be the bottom up parsing and another one is going to be the top down parsing. Actually what they say, if the parse tree is constructed from top to bottom, that is if you start with the root of the tree and if you continue to the leaf nodes available in the parse tree, then it is called top down parsing. But whereas if you start with the leaf nodes and continuously building the tree towards the root, then it is called a bottom up parsing. So the tree can be constructed, that is your parse tree can be constructed both top down approach and bottom up approach. So if top down approach is followed, we call the parsers as top down parsers. If bottom up approach is followed, then we will be calling the, that is a construct, that is our parsing process, bottom up parsers. So within the top down parsers and the bottom up parsers, we have some parsing techniques. If you look at the, that is your bottom up parsers, we have two major parsing techniques. One is the shift reduce parsing and another one is called the operator precedence parsing, and these two do not construct parsing tables. As far as shift reduce parsing is concerned, so it will construct the, or it will does the, it is doing the parsing with the help of a symbol, that is derivation called the rightmost derivation, which will be produced by the parser. So with the help of the rightmost derivation, the shift reduce parsing will find whether a string is accepted by the parser or not. But whereas in the case of there is where operator precedence parsing is concerned, it will construct a relation table among the various operators available in the grammar, and based on that the various actions will be carried out. We should know what are the various possible actions. That is, a parser can do, the first action is going to be the shift action, which means on seeing a token from the source program, it will be shifted onto the stack. But the next action is going to be a reduce action, that is on seeing a token, the token will be left there itself, but the already recognized tokens or the already processed tokens which are there on the top of the stack will be considered for a reduction by assuming that a handle is there on the top of the stack. So we should know what a handle is. It is going to be a sequence of tokens, and that will be eligible only if that particular part is available as the right hand side of a production. So that is what the reduce action. And another action is reporting error. So if the parser finds that it cannot proceed further, or if it fails to construct a parse tree, it will report error. And the final action is going to be an accept action. So when we find that the parse tree is successfully constructed and there is no more token available in source program, that is from the input, the parser will say that the program has been accepted, saying that successful parsing process. These are the four possible actions. So if these actions are decided based on the relation table which was constructed by an operator precedence parsing process, then we will be calling it as operator precedence parsing. So these two are the bottom up parsing techniques, and there is a major class of bottom up parsing called LR parser. So that is the most efficient one. So within that also we are having three classes of parsers, and we shall see the classes of top down parsers, but after a short break. Welcome back. So we have seen the various parsing techniques available in the bottom up parsers. Now, to see the various parsing techniques available in the top down parsers, actually we are having two major parsers. One is called the recursive descent parser and another one is called the predictive parser. We know that the top down parser constructs a parse tree in a top down approach. It will start from the root and it will proceed towards the leaf nodes. On all branches, if you are able to reach the leaf nodes, then we can say that the parsing is over. But if that construction is done with the help of a collection of recursive procedures, then we will be calling them the parsing process as a recursive descent parsing. That is, a recursive descent parser constructs the parse tree by expanding continuously recursive procedures. But there is a major drawback with this. More the depth of the parse tree, more the depth of your recursion, and more the depth of the recursion, the stack which is being followed or used for handling the recursion will be that is used. So, more the depth, more entries onto the stack. So, at some stage we will find that the stack overflow kind of things, then your compilation will abruptly stops. So, there is a reason or there is a problem we face with recursive descent parser. But whereas we have an equivalent parser which is doing the same job, that is a construction of the parsing process, but with the help of a tabular version where the stack is managed by the compiler itself, that is a parser itself, but not by the stack which is controlled by the program translation. So, here the complete entries are available in the tabular format, we call it as a predictive parsing table, and the various actions are also incorporated into the predictive parsing table. The actions I mean the shift, reduce, accept and error, they all are propagated into the parsing table itself. So, from the parsing table we will be able to know what kind of action is going to be suitable for the current context. So, this is what the major classification of the that is parsers, and we know that the parsers are making use of the grammars for the construction of the parsing table or even for the parsing also. So, first you should know what is a context free grammar. So, it is going to be a system with 4 components. One is the terminals, another one is the non terminals, and the third one is going to be start symbol of the grammar, and the fourth one is going to be productions. So, the terminals are actually the basic symbols from which the strings are formed. Here we should know what is the meaning, what we mean by string here. The parser is supposed to get the stream of tokens. The tokens are actually formed with the help of symbols. For example, you can take a keyword called else. It has 4 symbols ELSE. So, when you are talking about the terminal, the else becomes a terminal here, and this will be considered as a single token. So, which cannot be further expanded. So, if you are going for a statement or an expression, for example, a plus b, we have 3 terminals. The first terminal is a, the second one is plus, and third one is b. So, these a plus b will be considered as string here. So, terminals are used for forming strings. So, whereas non terminals are used for describing the syntactic variables. So, if I say that an expression a plus b is there, it is being referred by a syntactic category called expression, we call it as otherwise called E. So, this E stands for an expression. So, this E is always called here as the non terminal. E by itself is not part of the program, but a plus b is part of the program, but E refers that expression a plus b. That is why we call it as the syntactic variable. And there will be a specially designated non terminal which is called the start symbol, and the set of all strings denoted by start symbol is nothing but the language of the grammar. So, if you take all the strings recognized by the start symbol, it will be considered as the language of the grammar. And most important component of the grammar is the set of all productions. So, that will be telling you that is how the terminals and non-terminals are related. For example, I said E is a non-terminal, A plus B is going to be the string containing 3 terminals. So, now to relate this non-terminal with the terminals, so we will need a rule. We know that an expression can be the expression plus another expression, or an expression can be simply an identifier. If you combinedly take these two rules, then we will be able to come up with a parse tree for A plus B, which is having a root called E, and then it will be expanded to E plus E. Then further these two E's are expanded to identifiers, where A is the first identifier and B is the second identifier. We will be having a tree. So, this tree construction is possible only with the help of the production rules. And what do we have in each production is a non-terminal on the left hand side. That is, normally you will be having the syntax called A derives alpha, where A belongs to non-terminal and alpha is the combination of variables and terminals any number of times, including 0 times. So, for different types of grammars, the rules will be having different constraints, but as far as context free grammar is concerned, the left hand side is strictly supposed to have only one variable, and the right hand side is supposed to have, that is, any number of terminals or variables including 0 times, but they all must be already predefined things, but you cannot all of a sudden introduce the terminals which are not there in the terminal set. So, that is what the rule, that is conditions for production rules. So, a grammar has 4 components. One is the terminal set, another one is non-terminal set, and third one is start symbol of the grammar, and the fourth one is going to be the production rules. So, here we have one that is grammar as an example. So, the grammar is meant for the arithmetic expressions. So, we have a set of rules. So, the expression is the expression plus another expression. We have an expression is formed by the sum of two expressions, that is our plus, or it can be the difference E minus t, and it can be the multiplication, it can be division, it can be the exponent, or it can be anything inside the bracket, or it can be an identifier. So, the f's deriving this, or f tends to I denotes. So, an expression can even be an identifier also. So, now we look at the rules for an identifier. One letter forms an identifier, or an identifier is already existing, along with that we are adding a digit, it will be still an identifier, or an identifier is already existing with which we are adding a letter, that is also still an identifier. So, now we should know what is a letter and what is a digit. A letter is going to be either A, B, C, D, etc. up to Z, and a digit is 0 or 1 or 2 or 3, anything etc. up to 9. But because of the recursive nature of these production rules, we will be able to form any identifier of any length, but they all are supposed to start with only a letter, since we are finally terminating with a letter alone, an identifier. So, now when you are looking at the productions, we see this grammar is going to be an unambiguous grammar. That is the reason why we find too many number of there is non-terminals, there is t is there, then p is there, then f is there. But if it is allowed to have an ambiguous grammar, then we can very easily write them as e plus e, e minus e, and e star e, then e slash e, and e exponent, that is e. And one important thing here we have to understand is, we have e plus t, that is e derives e plus t here, and t derives t star p here, but whereas p derives p to the power that is f. So, there is a mistake here, and it is not going to be p to the power p to the power f, p derives p to the power f, it should be p deriving f to the power p. It is because of we find that plus, multiplication, then it is going to be subtraction, division, they are all the left to right associative productions or operators, but whereas exponent is concerned, its associativity is not from left to right, but it is from right to left. So, we must have this as a production called P derives f to the power p. So, that it will be that is recognizing the strings with right to left associativity for all exponentiation operators. So, here is the that is the expression which we call it as an expression inside bracket. Whenever we want to change the priority of an expression or priority of an operator, then this comes into the picture. So, for example, if you are having an identifier then like followed by an plus followed by another identifier, that is for example, it is going to be a plus b multiplied by c, the default that is priority and associativity will be multiplication takes more priority than addition, but if you want to change the associate, that is your priority, like plus is to be carried out first followed by multiplication, then we will try to put a plus b inside bracket. So, in such kind of scenarios we need to have the productions f derives opening bracket e closing bracket. So, that is the reason why we are having the that is expression inside bracket, which is meant for changing the default priorities of the operators. So, to summarize the meaning of parser, and then we have seen context free grammar also. Parser, it is a program which is recognizing the syntax of the program, and grammars are used for describing the syntax of programming language constructs or syntactic constructs. To the question component, the role of parser is important, and what is going to be the output of any parser, and you can even be asked to construct, that is how the parsers are constructed. So, you will be asked to write grammars for various constructs, maybe for an if statement or even for there is an assignment statement or expression or even for declarations. So, they are all coming into the programming language constructs. So, for every programming language construct, it is possible to come up with a context free grammar, so that we will be able to that is generate the language or the set of all statements of that language. So, this is what about the various types of questions as far as this particular episode is concerned, and with this I conclude this episode. Thank you all.